Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the online lecture of control systems theory. Today we are going to talk about stability, the concept of stability for control systems. So this stability is part of the analysis of systems. So in the course of control systems theory, there are basically three parts. First part is modeling, second part is analysis, and the third part is design. So we have been through the modeling part, where we have discussed different ways of modeling control systems, and now we are starting the analysis part. And in the analysis part, we are first of all we are going to study the stability analysis. So first type of stability that we are going to discuss today is the input output stability. Input output stability is related to the input and output signals applied and obtained from the systems respectively. So among the input output stability, the particular type of stability that we are going to discuss is bounded input bounded output stability. As the name suggests, this stability basically requires that if your input of the system is bounded, then this should result in a bounded output. In other words, no output of the system should be unbounded or infinite unless the input itself is infinite. So how do we mathematically represent this stability, or how do we mathematically state this stability? Is the following. It states that if the norm of the input signal u of t is less than or equal to some quantity m or upper bound m, which is finite, then this should imply that the norm or magnitude of the output signal y of t should be bounded by some finite number or quantity n. So this is a way of mathematical way of saying that the bounded input should always imply bounded output. The value of the bound could be as large as, it could be large or small, it does not matter, as long as it is finite. So the norm is basically magnitude. It's for scalars, it is like absolute value, and for signals of time, one way of calculating the norm is, for example, if you want to calculate the norm of u of t, then it would be, one way of doing that would be to find the maximum over all t for of the absolute value of u of t. So it will be like the absolute value of peak of u of t with respect to t. That peak could be negative or positive. When you take absolute value, everything becomes positive, so the norm is always positive. Okay, so this is BIBO stability. Let's look at some examples in order to clarify our concept. For example, let us suppose we have a system where y is equal to some constant times input u. Now if we wonder if this system is BIBO stable or not, you have to look at the equation and try to figure out a value of u for which, a finite value of u for which y will become infinite. So as long as k is non-zero, as long as k is some positive or even a negative number, y cannot be infinite unless the u itself is infinite. So we conclude that this system is BIBO stable. Similarly, if y is equal to k times u square, even this system is still BIBO stable, because if we assume that k, the constant k is non-zero, then basically any finite value of u, its square will also be finite. So if you multiply that square with the constant k, the product will still be finite. So there is no way of having y to be infinite with finite value of u. So this system is also BIBO stable. Similarly, y is equal to sine of u. We all know that sine of u varies between 1 and -1, so it does not go to infinite value. So for whatever the value of u is, the y is equal to sine u is BIBO stable system. Next we look at y is equal to tangent of u. Now this is a special system because tangent of u becomes infinite when u is equal to pi by 2. When u is 90 degrees or pi by 2 radians, the tangent will become infinite because tangent is sine over cos, and cos at pi by 2 is 0 and sine at pi by 2 is 1, so 1 over 0 is infinity. So this system is BIBO unstable because pi by 2 radians is a finite value of u for which y will become infinite. So this is one example of BIBO unstable system. Similarly, if y is equal to 1 over u square minus 1, then you can see that if u is equal to plus 1 or if u is equal to minus 1, the square of u will be plus 1, and 1 minus 1 in the denominator will result in infinite value of y. So this system is also BIBO unstable. So these are the examples of BIBO stable and BIBO unstable systems. Next we look at the theorem, the mathematical result which will help us in calculation of BIBO stability. Recall that in these examples we just calculated BIBO stability with our intuition. But how should we calculate BIBO stability for linear systems that we have discussed in this course? Like for example, if a transfer function is given to us, how do we calculate the BIBO stability? So for a LTI system, an LTI system is BIBO stable if and only if its unit impulse response is absolutely integrable. Absolutely integrable means that if you integrate the unit impulse response, the absolute value of unit impulse response from 0 to infinity, then the result should be finite. That is what it means for unit impulse response to be absolutely integrable. So recall that unit impulse response is the impulse inverse Laplace transform of transfer function. So if you have a transfer function of an LTI system, you take its inverse Laplace transform and take the integral from 0 to infinity of the absolute value of inverse Laplace transform, and then you will see if it is finite, then the system will be BIBO stable, otherwise the system will not be BIBO stable. So we can do an example here. Let's say consider a transfer function 1 over s plus 3. This is a first order transfer function. If we take Laplace inverse, so there is we can use the standard Laplace table for calculating this inverse, and we can find easily that the inverse Laplace of 1 over s plus 3 is e raised to the power minus 3t. And when we integrate the absolute, so since e raised to the power minus 3 is always greater than or equal to 0, so its absolute value is equal to itself. So when we integrate this absolute value, we get, like when we put the limit infinity, we get 0. When we put the limit 0, we get 3. So the total integral value is plus 3, which is less than infinity. Therefore g of s equal 1 over s plus 3 is BIBO stable system. Similarly, you can find BIBO stability for any transfer function as long as you can calculate the inverse Laplace transform of that, and you calculate the integral of that inverse Laplace transform. Then you can find out whether a system is BIBO stable. Okay, so now that we have looked at BIBO stability, next we look into the internal stability or Lyapunov stability of the system. The internal stability of the system is the property of equilibrium points in a system. So we have already discussed the equilibrium points when we discussed the linear approximations of nonlinear systems, but let me just remind you what an equilibrium point is. An equilibrium point is a value of state vector x for which the derivative of the state vector becomes 0. This is basically the value of state vector for which the dynamics or the changes in the states are 0. So if a system is starts from equilibrium point, it will stay at equilibrium point forever, because at the equilibrium point all the dynamics, all the rates of change are zero. So rates of change being zero means that it is, you can also call it a static point. Some people call it critical point. So there are many names for this point: static point, equilibrium point, critical point, and maybe more. Okay, so but the important thing is that you understand its definition. So by definition, it is a point at which the all the dynamics, all the rate of change of in the system are zero. So to calculate the equilibrium points, you have to solve the equation f of x equals 0 or ax equals 0, which is basically another way of saying that x dot equals 0. So how do we define the internal stability of a system? Internal stability of a system basically is defined with respect to equilibrium point. The equilibrium point x star of a system, x dot equal f of x or x dot equal a of x, is stable, or stable in the sense of Lyapunov, if for all epsilon greater than 0 there is delta greater than 0, such that if the distance between initial condition and the equilibrium point is less than delta, then that implies that the distance between x of t at any time from the equilibrium point is less than epsilon. So basically what the definition of stability is asking or requiring is that if your initial so you have to keep in mind that a state is a function of time. So because the system is represented as x dot equal a of x. I'm talking about linear system. If you talk about linear system, then this is a linear dynamical system. Dynamical system means the system that has some dynamics that changes with time. So x dot equal a of x means a into x means that x will change with time. Derivative of x with respect to time is non-zero. So x will change with time. So if you solve the differential equation, you solve it using some initial condition, so or boundary values. So the stability requires that if the initial condition of the state vector is close enough, like if it is within delta distance from the equilibrium point, then this should imply that the trajectory, or you can say the value of a state vector with respect to time which is changing, it may change in whatever way possible, but it may not go much like farther away from the equilibrium point, farther than the epsilon value. So the distance between state at any time from the equilibrium point should not be greater than or equal to epsilon if the initial condition is within delta distance from the equilibrium point. Okay, so next is the definition of asymptotic stability. So far we have looked at the definition of stability or simple stability. Next we look at the asymptotic stability definition. So equilibrium point x star of a system, x dot equal f of x or x dot equal a times x, is asymptotically stable in the sense of Lyapunov if number one, it is stable, like if it satisfies the conditions of stability, and number two, there should be additional condition satisfied by this system to be asymptotically stable, and that additional condition is that there exists some value eta such that if the initial condition is within eta distance from the equilibrium point, then your trajectory should converge to equilibrium point as time approaches infinity. So this is basically saying that your trajectory or your state values with the passage of time or asymptotically should converge to the equilibrium point. So this expression that x of t approaches x star as t approaches infinity, you can say it in the following manner, that x of t approaches x star asymptotically. So that is why the name asymptotic stability comes. Okay, So asymptotic stability is stability plus an additional property that if the initial condition starts within certain eta distance from equilibrium point, not only that it stays close enough, but it does more than staying close enough. It basically converges to the equilibrium point. So then there is finally the definition of global asymptotic stability. Global asymptotic stability is an equilibrium point x star is globally asymptotically stable in the sense of Lyapunov if it is asymptotically stable with eta equal infinity. So eta was the region. So global asymptotic stability means that no matter where your initial condition is, no matter where your initial condition is, your trajectory will always converge to the equilibrium point. So for simple asymptotic stability, there is only a certain range about the equilibrium point within which the trajectories converge to equilibrium point. But global asymptotic stability requires that the range, like there is no range, the range is infinite, which means that no matter where you start, you end up converging to the equilibrium point. Alright, so next we look at into the definitions of these stability in a little bit of more detail, because it is very important that you clearly understand the definitions of stability and what they mean for the systems. So first we look at the definition of stability in the sense of Lyapunov, where the requirement is that if the norm or magnitude of x of 0 minus x star is less than delta, then this should imply that the norm of x of t for any time minus x star should be less than epsilon. So this is the picture that basically shows this concept. If you look at this is a plot between x of t versus time. So I'm assuming like scalar single state variable. If you understand it for the single state variable, you can understand it for all multiple state variables as well. So if x of t is a scalar and you plot it as a function of time, then this definition of stability is basically has a few components. First component is x star. So I have drawn a black black horizontal line, which is a thin one at the value x equal x star. So this is the reference for x equal x star, and then in the neighborhood of x star there is a delta band. So there is the delta band is represented by dashed and dotted black lines, and so this is a neighborhood of x star. If you start, if the trajectory has been plotted in the color blue, so if the trajectory starts within the delta neighborhood of x star and it stays within epsilon neighborhood for all time, then the system is asymptotically stable. But here I also have to emphasize on the fact that for all epsilon there exists some delta. So the situation that you can see in the diagram on your screens, this situation should be for any possible width of delta and on any possible for any possible width epsilon. So for any possible width epsilon, no matter how small the epsilon is, there should be some corresponding delta, such that if you start within delta distance from the equilibrium point x star, then you are guaranteed to stay within epsilon distance within from the x star. So for all epsilon there exists some delta. So this is very important to understand, because it is like if you want to prove the stability of the system, you have to prove it for all possible epsilons, and all possible epsilons are infinite. And we will see that how we calculate the stability, because calculating the stability of a system using the definition of stability, that is not always possible or even like feasible to do, because if you look at the definition requires that we test all possible epsilon values, and for all possible epsilon values there should exist some delta, such that if you start within delta distance from the equilibrium point, you stay within epsilon distance from the equilibrium point. So if you summarize the definition of stability, then you can say that if you start close enough to x star, then you stay close enough to x star. So that is, if you have that, then you have stability. Then we look at asymptotic stability. Asymptotic stability requires that not only we start and stay close enough, but we also have another neighborhood around the equilibrium point eta, such that if you start within this neighborhood, you basically converge to the equilibrium point. Now if you look at the blue line, it starts within the neighborhood epsilon and it basically converges to the equilibrium point value, although it never becomes exactly equal to the equilibrium point because of the existence and uniqueness of solutions of differential equation. So it will never cross the equilibrium point or touch the equilibrium point, but as the time goes on, it will come closer and closer and closer to the equilibrium point. So we say that x of t approaches x star as t approaches infinity. So this is the concept of asymptotic stability, that it is stability plus the some neighborhood existence eta, such that if you start within eta distance from the equilibrium point, then you converge to the equilibrium point. The trajectory should converge to the equilibrium point. So this eta you can refer to as region of attraction. So region of attraction is a region around the equilibrium point from where if you start within the region of attraction, you are attracted to the equilibrium point. If you start outside the region of attraction, you may not be attracted to an equilibrium point, but at least you will have the epsilon delta stability everywhere, no matter where you start. Okay. So if the region of attraction is infinitely large, then you have global asymptotic stability. Okay, so now we come to the point where we look at the interpretation of stability for linear systems, and especially linear time invariant systems. So in order to calculate the stability of linear time invariant systems, we look at something like, for example, if a linear time invariant system is represented in terms of a transfer function, then the denominator of the transfer function, if you put the denominator polynomial of the transfer function equal to 0, then that is called characteristic equation of that transfer function, and roots of the characteristic equations, the characteristic equation are called poles of the system. And the stability of a linear time invariant system is calculated with the help of poles of the system. So in order, if you want to determine the stability of an LTI system, whether it is stable, asymptotically stable or globally asymptotically stable, you have to calculate the poles of that transfer function, the transfer function of the linear time invariant system. And once you calculate the poles, then the location of the poles will tell you whether the system is asymptotically stable or globally asymptotically stable. Remember, I already told you that it is not always feasible to calculate stability using the definition of stability. So instead of using definition, we use this pole technique. So if the system is in state space format, then we calculate its stability with the help. Then its characteristic equation becomes determinant of S into identity matrix minus A matrix. So determinant of Si minus A, if you put equal to 0 and solve for the roots of S, like it will become a polynomial of S, and it will be the same polynomial of S as is the transfer function. So remember that in stability we do not consider the control part, because the control part has the capability of changing the stability property. So we can actually make an unstable system into a stable system with the help of control, and we can also destabilize a stable system with the help of control. So here we are not mentioning control so far. and we are also only looking at the natural dynamics. So x dot equal ax is called the natural dynamics of the system, and we calculate the stability from the natural dynamics. So you can either calculate the poles from the denominator of the transfer function, or you can calculate the poles from the this is the eigenvalues of the matrix A. Determinant of Si minus A equals 0. The roots of this equation will be the eigenvalues of matrix A. So you can calculate the poles from the eigenvalues of matrix A, or you can calculate the poles from the denominator polynomial, the roots of the denominator of transfer function. Okay, now let us look at the poles in a little bit of more detail. Let us suppose that you have an nth order transfer function, and then an nth order characteristic equation will have n poles. So if you have n poles, call them lambda 1, lambda 2, lambda 3 up to so on lambda n. Then each of the pole can have real or imaginary parts. So let me just state this, that if the characteristic equation has real coefficients, which is the case for almost all the system that we study in this course, then poles can either be real, or the poles can be in the form of complex conjugate pairs. So the poles will be either real poles or complex conjugate pair poles. So if the pole is a complex conjugate pair, then it will have like a complex pole will have two parts, a real part and an imaginary part. So if you write a complex pole as A plus J into B, then A will be the real part and B will be the imaginary part. So here I have written lambda I equal ai plus j into bi, where I could be 1, 2, 3 up to so on n. So lambda I could be like I could be 1, then this is lambda 1, if I is 2, this is lambda 2, and so on. So there are n poles, so there are n lambdas. A linear system is asymptotically stable if the real part of all the lambda I, if the real part of all the poles is less than 0. If the real part, so if you calculate the poles of a transfer function, or if you calculate the poles using the eigenvalues of the matrix A, then if the real part of all of your calculated poles is strictly less than 0, then you are guaranteed that your system is asymptotically stable. So in order to calculate whether the system is asymptotically stable or not, you have to calculate the poles of that system and determine if the real part of all the poles is less than 0 or not. Even if one of the poles has real part greater than or equal to 0, then it will not be asymptotically stable. For linear systems, asymptotically stable and global asymptotically stable is the same thing. So nonlinear system could have a finite region of attraction, but linear systems, if there is a region of attraction, it is always infinite. So this is some simplification for linear systems. For linear systems, another thing is that all equilibrium points of a linear system have same stability property. So therefore linear system stability is basically, you can say that the system is stable rather than saying that the equilibrium point is stable. For nonlinear systems, different equilibrium points may have different stability property. One equilibrium point may be stable, another may be unstable, another may be asymptotically stable. But for linear system, if one equilibrium point is asymptotically stable, then all of them are asymptotically stable. If one equilibrium point is unstable, then all of them are unstable. If one equilibrium point is simple stable, then all of them are simple stable. And usually it also can happen that a linear system may only have just one equilibrium point. This is the situation, that in order to calculate the asymptotic stability, you calculate all the poles, and if the real part of all the poles is strictly less than 0, then you have asymptotic stability in the linear system, which means no matter how many equilibrium points it has, all of the equilibrium points are globally asymptotically stable. So next we have interpretation of stability for linear systems. um, so far we have looked at the asymptotic stability. Now we look at the just normal stability. So if you look at the normal stability or just stability, a linear system is stable in the sense of Lyapunov if the real part is less than or equal to 0 for all the poles. If all the poles have real parts less than or equal to 0, and the poles with real part exactly equal to 0 are simple, like non-repeated. There should be no repeated poles with real part equal to 0. So if there is a real for linear systems, in order to find out whether it is stable or not, you have to see, first of all you have to see that all the poles should have the real part less than or equal to 0, and then you have to look at all the poles which have real part exactly equal to 0, and you should verify that none of those poles have same imaginary part. Like the poles should not be repeated. For example, let's say if a system has 4 poles, lambda 1 is at -3, lambda 2 is at 0 plus 2j, and lambda 3 is at 0 minus 2j, and lambda 4 is at 0, then you can see that 3 of the poles have 0 real part and one of the poles have negative real part. So this system is just simple stable. Why is it simple stable? Because all the 3 poles having 0 real part, one has an imaginary part plus 2j, another has imaginary part minus 2j, and the third one has imaginary part to be equal to 0. So all 3 have different values of imaginary parts. No imaginary part is repeated for 0 real part poles. So this system is stable. Similarly, if a system has like lambda 1 equals 0, lambda 2 equal 0 plus 2j, lambda 3 equals 0 minus 2j, and lambda 4 equals 0, then in this case the system is unstable because lambda 1 and lambda 4 both have real part 0 and the imaginary part is also the same. So these are repeated poles with 0 real part. So this system is unstable. This system is not stable, and I'm sorry about this typo in this in these 2 examples, because lambda 2 is written twice here. I correct it here that the lambda 2 is 0 plus 2j in both examples, and lambda 3, so 0 minus 2j in both the examples is lambda 3, not lambda 2. Okay, so the third example is that let us suppose we have lambda 1 equal minus 2j, lambda 2 equals 0 plus 2j, and again lambda 3 should equal 0 minus 2j, and lambda 4 equals 2j. So in this case you can see that lambda 4, all the poles have 0 real part, and there are 2 repetitions. Lambda 1 and lambda 3 have same imaginary part and 0 real part, and lambda 2 and lambda 4 have same imaginary part and 0 real part. So there is 2 repetitions, and we lose stability even if there is 1 repetition. So here there are 2 repetitions, so we definitely lose the stability property. The system with this type of poles is not stable. So now we have established the definitions of stability, asymptotic stability, BIBO stability, and we have discussed all the types of stability that are within the scope of this course. So now at the end, let us look at the relationship between different types of stability. This will help you in understanding how different types of stability are related to each other. So first of all, asymptotic stability implies BIBO stability. So you have to see that this means that if a system is asymptotically stable, then you don't have to calculate BIBO stability for that system. It is understood that an asymptotically stable system is always BIBO stable as well. Similarly, asymptotic stability also implies simple stability, which basically, if you look at the definition of asymptotic stability, it requires the system to be stable. So if a system is asymptotically stable, then it is automatically guaranteed that it would be stable as well. Next is that the stability does not imply BIBO stability. So if a system is simple stable, not asymptotically stable, then you do not know anything about the BIBO stability property of that system, and you will have to calculate the BIBO stability separately. Next is BIBO does not imply stability. So it is just that if you know that the system is BIBO stable, it does not mean that it will be stable in the sense of Lyapunov. You have to calculate the stability in the sense of Lyapunov even if you know that the system is BIBO stable. BIBO stability does not imply asymptotic stability, and that should be almost obvious, because if the BIBO cannot even imply simple stability, how can it imply asymptotic stability? If I summarize all of these points, then you can see that this picture depicts which type of stability implies which stability. So the red lines basically show that the implications are not there. So for example, if you look at the asymptotic stability AS, then AS implies BIBO and it implies simple stability, and the stability and BIBO do not imply AS. And if you look at the arrows between BIBO and simple stability, neither of them imply any other stability type. So this is all that I wanted to discuss about the stability. I just want to recap that in this lecture we have just started from the input output stability. We looked at the BIBO stability, its definition, that the system is BIBO stable if finite input implies finite output. Then we looked at some examples of the BIBO stability, and then we look at how to calculate BIBO stability for LTI systems, and we looked at an example of that. And then we looked at the definition of internal stability. First of, we looked at the definition of equilibrium point, because that's important for studying internal stability. Then we looked at the definition of the internal stability, the epsilon delta definitions. Remember that the difference, the magnitude of difference is basically distance. So if I say x of 0 minus x star norm, then this basically means that the distance between x of 0 and x star. Then there is definition of asymptotic stability, definition of global asymptotic stability. We looked at the conceptual, we tried to understand the concept of stability using this diagram, where we show the delta bounds and epsilon bounds. And you have to remember that the stability requires that for all possible epsilon bounds there should be a corresponding delta bound, and only then the system will be stable. Even if there is a single epsilon bound for which there is no corresponding delta bound, the stability will be violated. So there is asymptotic stability, which is characterized by region of attraction. Then there is global asymptotic stability. Then there is interpretation, the calculation of poles using transfer function, and calculation of poles using state space. So from transfer function, this is the roots of the denominator of transfer function, and for state space is the the poles are the eigenvalues of the matrix A. And then we see that poles could have a real part and imaginary part, and asymptotic stability requires that the real part of all the poles should be less than 0, strictly less than 0. And for linear systems, asymptotic stability implies global asymptotic stability. Then we looked at the simple stability. Here you notice that the simple stability condition is a little bit relaxed compared to the condition of asymptotic stability. Asymptotic stability does not allow the real part to be 0. It requires that the real part should be strictly less than 0. But simple stability allows the real part to be equal to 0. But whenever the real part is equal to 0, the imaginary part cannot repeat for more than one poles. So that's the condition for simple stability. And then we looked at the relationship between BIBO stability, asymptotic stability, and internal stability, like simple internal stability. So I hope you were able to understand or grasp the concept. If not, you are welcome to ask any questions.